four towards asymptotically efficient mechanisms with a guarantee on the expected gains from trade by Moshe, Babaioff, Yannai, Gonczarowski, and Mingfei, Zhao. And Yannai is giving the talk.
Thanks. Can you hear me over there with the camera? Great. Okay. Thanks for staying in your coffee break, and let's start. So, in a bilateral trade setting, we have one seller and one buyer. The seller holds a single item. It has a private non-negative cost for parting with the item, and this cost is sampled from some distribution D. And a potential buyer has a private value for obtaining the item, which is also independently sampled from some other distribution. And both agents have quasi-linear utilities and are risk neutral. It means that if the item is sold, then the seller's utility is the revenue that she gets minus her cost, and the buyer's utility is her value minus what she paid, and everyone cares only about expectations. We say that it's efficient to perform a trade when the buyer's value is higher than the seller's cost, and would like a mechanism that is individually rational, that is, all expected utilities are always greater or equal to 0. It's truthful. It's weakly budget balanced, meaning that it does not lose money. You can think about it as IR for the auctioneer, if we're talking about incentives of the auctioneer, and also efficient. So let's talk about everyone's favorite mechanism, VCG. So we can do VCG, which means trade if and only if B is greater or equal to S and charge threshold values. For these specific numbers, the buyer's threshold value is 9. If his value is greater or equal to 9, then there's trade. So she must be paying 9. The seller's threshold value is 10. If her cost is less or equal to 10, then there is a trade. So she must be getting 10. So someone must subsidize the mechanism which runs a deficit of 1, and generally VCG is not budget balanced. So there's actually a more general impossibility result due to Meyerson and Satterthwaite that says that no mechanism can be individually rational, incentive compatible, budget balanced, and efficient. I'm going to skip the whole ex-ante ex-post stuff for this talk. The CS approach, of course, is approximate efficiency while maintaining all of the other incentive participation constraints. And indeed, Blumrosen and Dubzhinsky, 2016, have given a multiplicative welfare approximation mechanism. Now, the thing with welfare is that even if you don't trade at all, you already have welfare. Without trade, the welfare here is 9, after it's 10. So not trading at all already in this scenario gives you 9/10 fraction of the maximum welfare, which seems kind of cheating. So one can look at the gains from trade instead. The gains from trade is the increment in the welfare compared to no trade. So in this case, no trade is 0 gains from trade. Trade means gains from trade of 1. And in particular, no trade is a 0 fraction of the maximal gains from trade. And note that while maximizing welfare is the same as maximizing the gains from trade, giving a multiplicative approximation to the welfare is not the same as giving a multiplicative approximation to the gains from trade. It's actually harder to give a multiplicative approximation to the gains from trade. So it's unfortunately not possible to ex-post approximate the gains from trade to guarantee that for every profile we're going to have at least half of the gains from trade. So we have two options. First option, add additional assumptions. There is a result by Blumrosen and Mizrahi that talks about MHR distribution, restricted class of distributions. Option number 2 would be to relax our benchmark. Instead of going for the first best, the VCG benchmark, I'm going to use first best and VCG intermittently in this, interchangeably in this talk. We can talk about the second best benchmark, which is the mechanism with the highest GFT among all IR, incentive compatible, and budget balanced mechanisms. So at this point, you must ask, okay, so why not use the second best mechanism? It gives a 1 approximation to your benchmark, which is the second best mechanism. So, well, the second best mechanism might be very, very complex. So the goal is to find a simple mechanism that gives a good guarantee compared to the second best mechanism. And there's a result by Brussel et al. 2 of the co-authors on that paper are shared with this paper, that gives a simple mechanism that gets at least 1/2 of the expected gains from trade of the second best mechanism. Let's review their mechanism. So it's very simple, randomly with probability 50/50. Either the seller gives post a take it or leave it price for the buyer, and if the buyer accepts, then there is trade at that price, and the seller chooses this price to maximize her utility, or symmetrically, the buyer posts a take it or leave it price to the seller. Take it or leave it offer to the seller if you wish. And they show that this mechanism, which we'll call ARVM, Random Virtual Welfare Maximizer for this talk, obtains a 1/2 approximation to the expected gains from trade of the second best mechanism. And to explain our goal in this talk, I'm going to have to go beyond bilateral trade. So we're going to have n buyers and n sellers. Till now, we only had one seller, one buyer. We're going to have homogeneous goods. All the goods are the same. All the values are independent. Each seller has one item. Each buyer wants one item. And we're going to have two settings. One of them is the double auction setting, where each buyer can trade with each agent. And the other more challenging setting is the matching setting, where we have a bipartite graph that defines the possible trades. So the ARVM mechanism, we're going to need that to understand the difficulty in answering the question that we'll ask. For the general setting, we still have a 50-50 probability of a seller offering or a buyer offering. The generalized seller offering mechanism is going to pick the allocation that maximizes the seller's total virtual surplus. So we're going to have the max weight matching with the edge weights are phi I, that's the iron virtual value of buyer I, of BI minus SJ. To get some intuition into this, because I don't have the scope to really give you the full proof, recall that if only I and J were in the market, then the optimal offer of seller J to buyer I would have been phi I inverse of SJ. And if it's accepted, then it means that BI is greater or equal to that, or equivalently that the edge weight is non-negative. So we're looking to kind of maximize the total virtual gap between the seller's costs and the virtual values of the buyers. So with the other probability 50%, same thing with the buyers. We get the iron virtual costs completely symmetric. And their main theorems that this is IR/IC, budget balance, and guarantees at least half of the expected gains from trade of the first best. Turns out, though, as we noticed, that this is not asymptotically efficient. Turns out that if we have a very large double auction, n buyers, very simple, all of them sampled IID from uniform 0, 1, the ARVM is going to lose a constant fraction of the gains from trade. It's never going to achieve asymptotically optimal trade. It's going to lose a lot of possible trades. And we can ask, can we get asymptotic efficiency by another mechanism? So enter McAfee, or rather enter McAfee before anyone else I've spoken with you about in this talk. And he gives the following awesome mechanism. So you sort all the buyers, you sort all the sellers. You look for the point where the sellers start to have cost higher than the buyers. So these three pairs are the first best, they're the VCG outcome. And McAfee says, well, drop the last pair. Only trade the first two pairs, but use the last pair to price the first two pairs. So both these sellers are going to get 45. Both these buyers are going to pay 60. And McAfee tells us that this is IR/IC, weekly budget balanced, and guarantees at least a 1 - 1 over Q fraction of the realized gains from trade. Okay, so it's weekly budget balanced since this pair could have traded, so 60 is more than 45. And the approximation is because out of Q pairs, we drop the worst pair. Now, this is asymptotically efficient. As Q goes to infinity, the guarantee here goes to 1. But there's no promise whatsoever when Q equals 1, and could be a large part of the valuation space where this happens. So the ARVM mechanism approximates the expected gains from trade, but is not asymptotically efficient. The trade reduction mechanism is asymptotically efficient, but does not approximate the expected gains from trade. Our question is, can we get the best of both worlds? Can we get a simple IR incentive compatible weekly budget balance mechanism for double auctions, even for matching markets, with both guarantees, an ex post asymptotically efficiency with respect to the first best mechanism, and ex ante approximation of the expected gains from trade of the second best mechanism. And our main result, such a simple mechanism exists not only for double auctions, but even for the more demanding matching market setting. And for the bigger picture, we have the optimal mechanism, which may be unattainable due to complexity or some other reason. We have approximation mechanisms with worst case guarantees. We have asymptotic optimal mechanisms, and we're looking for this in between. We're doing this here in terms of gains from trade. We think that it's going to be a very interesting research agenda, also generally in other settings, mainly because a lot of mechanisms that give worst case guarantees do not have good asymptotic performance, and therefore they're unappealing to practitioners. And we hope that such best of both worlds mechanisms are going to have both nice theoretical guarantees and be far more appealing to practitioners. So the naive approach, if you want to do something like this, probably cross the minds of like at least 20%, if not 80% of everyone in the audience. Stitch the mechanisms together. See what Q is, the size of the efficient trade. If it's more than 2, write trade reduction. 1 minus 1 over Q is going to be more than half. Guarantees half. Else, run the ARVA mechanism. Guarantees half. Overall, you get half, and you get asymptotic efficiency, and everything's great. So not quite. Let's look at this example. So the buyers are drawn from these distributions. Think of the sellers as constant, if you wish, with this example. If B2 is 98, then the efficient trade is this. S2 trades with B2, S1 with B1. Trade reduction runs. We reduce the second pair. Buyer 2 gets 0 utility. What happens if B2 reports that she has 80? Then Q equals 1. It's only this. This is the efficient trade. So we run the ARVA mechanism. And it turns out that the ARVA mechanism, when the seller offers trades on this edge, because ARVA maximizes virtual surplus. And it turns out that the virtual value of B2 is higher than the virtual value of B1, even though the value of B1 is higher. And this is crucial in the proof of the ARVA mechanism in order to achieve their half approximation. So it turns out that the mechanism is not monotone. By reducing her bid, B2 increased her winning probability. Turns out, we show this in the paper, that it's not even interim monotone, so you can't even use any smart payments to get Bayesian incentive compatibility here. And the problem is that for Q equals 1, the ARVM may trade on a pair that is not the first best pair. So our approach here is to modify ARVM to trade only on the first best edges, to only offer trades on the first best edges. And the rationale here is that an agent can only cause a switch from Q greater or equal to, the case where we run the trade reduction, to Q equals 1 by removing herself from the first best. If we modify ARVM to only offer trades on the first best, then removing oneself from the first best is never going to be beneficial. The challenge is that following these modifications, we are far more restricted than the original ARVM mechanism, but we still need to give a multiplicative guarantee on the gains from trade. So we still need to have gains from trade at least as high as that of ARVM, maybe with some constant probability. We're going to lose a half here. So observe that the ARVM edge in this specific example has positive gains from trade. So B2 is the threshold price for B1 to be in the first best, right? Because if B1 drops too much, B2 is going to be in the first best. B1 has to beat B2 to be in the first best. And similarly, in this case, S2 is the threshold price for seller 1 to be in the first best edge. So we're going to run a random offering mechanism on the first best pair, buyer 1 and seller 1, where all the offers are going to be restricted between B2 and S2. Essentially, we're telling B1, okay, you're in the first best pair because you bid above B2. Now we can't make an offer to whoever you're facing that's less than what you had to bid in order to get into the first best pairs, because otherwise we're going to lose on incentives. So actually doing this gives us incentive compatibility. It means that no one who is below the threshold for the first best pair has any incentive to deviate to be in the first best pair. But also it gives us the guarantee, the challenge that we talked about, the guarantee that we're going to get at least half of the welfare of ARVM. Why is that? Because if ARVM trades on the red edge in this specific example, then it means that B2 is greater or equal to S1. Otherwise, that edge would have negative weight. That means that since buyer 1 offers at least B2, buyer 1 offers at least S1. So trade occurs because seller 1 is going to accept. That's the heart of the argument. So the final combined mechanism for any set of bids, calculate Q. If Q is greater or equal to 2, run trade reduction, and run the random offering mechanism on the pair B1 and S1, where with probability half, seller 1 offers a price between B2 and S2, and with probability 1/2, buyer 1 offers a price between B2 and S2. And this is an IR BIC ex-post weekly budget balance mechanism that satisfies both of the following the expected gains from trade of this mechanism is at least 1/4 of the expected gains from trade of the second best, and this mechanism guarantees at least a 1 minus 1 over q fraction of the realized first best gains from trade. I've given you a little bit of hints into the big proof. It needs more care than that. There is some issue that I've glossed over. And as I said, the quarter approximation comes from either Arvum and the first best edge go on the same edge, then you get the full welfare of Arvum. Otherwise, you lose 1/2 for a total of 1/4. So for matching markets, that's the more challenging scenario. We have a bipartite graph that defines who can trade with who. And our main result is actually a generalization of this result, getting a hybrid mechanism that is the best of both worlds for also matching markets. And it's going to be a strict generalization of what I've showed you before. So the first step is to generalize McAfee's trade reduction to matching markets. McAfee's paper only deals with double auctions, so I'm not going to go into that now. I invite you to take a look at the paper. But note that even to define what asymptotically efficient means, you have to be careful, because it's not enough to say the trade size goes to infinity, because you can trade you can take the union of many disjoint bilateral trades, and obviously you can't guarantee anything there because of Myerson-Sadat weight. So you have to be careful when you think about what makes sense as asymptotic efficiency. So once again, Arvum gets 1/2 of the second best, but we cannot stitch it with our generalized trade reduction due to incentives, once again, like the example we've seen before. So our step 2 is going to be to develop an offering mechanism that trades only on the first best edges and guarantees at least 1/2 of the GFT of Arvum. And finally, we're going to stitch these together as in the double auction case. So we're going to focus on the step 2 in the 2 minutes that we have remaining. So the Arvum mechanism may trade on different edges than the first best edges, so we need to cover them. So like before, the idea is that for each pair in the first best, we're going to run some offering mechanism, and like in the double auction case, we're going to have some offer constraints to increase the probability of trade. So recall that in the double auction setting, we had the constraints of offers being between B2 and S2. Problem is that it's not clear what the analogs of B2 and S2 should be now, because it's not like that for each seller, I as a buyer have a unique competitor. Maybe I can push someone around and my competitor is at the end of some weird chain where only each person can trade with the next one or whatever, so it's odd. So we need to find constraints to serve in the role of S2 and B2 for matching markets. For incentives, these must be independent of the reports of INJ. They shouldn't be able to affect the constraints on them or on the person giving them the offer. And they should also coincide with the threshold prices, both for incentives and to get the guarantee, as we've seen before. So I think this is the definition that took us the longest to write in this paper. And it turns out that the generalization of S2, we call it S bar, is the threshold for buyer I to be in the first best in the market without seller J. So let's say that again. Let's see why it's a generalization. So S2 is the threshold, if you think about double auctions, for bid for B1 in the market without S1. So without S1, B1, in order to be in the first best, needs to trade with S2, needs to offer at least S2. So it turns out that this definition, which is a bit cryptic, captures exactly what you need even in the very involved matching market setting, and same analogous definition for a B bar. So we're going to run a random offering on each edge of the first best and restrict the offers to be between B bar and S bar. There's also a lot of technical analysis going into why we indeed get at least half of the gains from trade of the second best mechanism. So recall that with double auctions, we only had one interesting case to talk about. We talked about this case for a while. Turns out that with matching markets, we have quite a few cases. So, and each of them is far more interesting. So our proof, I invite you to read the details on our paper, showed that some of these cannot happen due to some reason. In some of them, like in the double auction case, we simply trade with constant probability on all the green edges, so they cover the red edges. In some of them, we will not always trade on all of the green edges, but due to some miracle, the green edges that we will trade on are enough to cover the red edges, always with probability 1/2. So to recap, I think that this kind of best of both worlds approach is going to be useful, is going to be interesting in other scenarios than gains from trade. I think that having guarantees on hard instances and good performance guarantees also on easy instances is going to make things far more attractive for practitioners, and I hope to see other people here interested in this agenda. Thank you very much.
We're a bit out of time. If there is a question, we can take one question and then we'll go to the coffee break.
Can you give an example of what an asymptotically efficient guarantee might sound like?
Of what? Sorry?
An asymptotically efficient guarantee might sound like in any setting besides gains from trade.
So I wouldn't think exactly about asymptotically efficient verbatim, but just think about, in any setting whatsoever, think about good guarantees on easy mechanisms. So it could even be some, you could even take it to the direction of saying like, so here's the mechanism, I have some guarantee on it not running more than 2 months on any instance, but I want it to run like a millisecond on easy instances. So I mean, don't think about asymptotic efficiency as the general thing, just think about good guarantees on easy instances, reasonable guarantees on any instance.
All right, let's thank all the speakers.
Thank you.